Okay, welcome to lesson 5. This is where we start to look at combining what we know and kind of applying it back to triangles to make sense of some triangles that we actually couldn't do in grade 10. So we'll start off by talking about the sine law, and then we'll move into talk about the cosine law in the next video. So we'll just break this up into two parts. The next video we'll do questions that require triangles with sine law and cosine law in learning target 5. Learning target 4, we're going to talk about the ambiguous case. So first off, we just want to talk about like the sine law in general, and so I just want to kind of paint the sine law picture. And so we do that with this question. Johnny argues you can still find the length of x. He's going to call it root 2 using SOHCAHTOA. And using SOHCAHTOA, like if he splits that triangle in half, he can use SOHCAHTOA to find out the opposite side is 1. That's actually a special triangle. And so that's where he says without a calculator. And then we know that the other sides are root 3 and 1. And we can use Pythagorean theorem to find out that that's root 2. Okay. And this is actually the logic here that we use for the sine law. To prove the sine law, we take a triangle that looks like this, A, B, and C. We cut the triangle in half, and we introduce another variable called h. So we know sine B is h over A, opposite over hypotenuse, and sine A is h over B, opposite over hypotenuse. We can rearrange. H is A sine B, and H is also equal to B sine A. And so that means that they're equal to each other. A sine B equals B sine A. And if you divide them out, we get sine B over B and sine A over A. And also we know that the reciprocal is also true. And actually, when we're using angles, we'll put the unknown in the top left. We'll use this version. And when we're finding sides, we'll use this version. I notice that there's 3. I'll only ever use 2 of the 3, and we won't use A, B's, and C's when we actually use triangles. We'll just plug in the numbers that we know. Sine law says basically when you divide a side by the sine of the matching angle, or the other way around, you get the same ratio wherever you do that in the triangle. So basically, the sine law is a formula, but it's a nice idea as well. If you divide an angle by a side, sine of an angle by a side, you get the same thing anywhere in the triangle. That's the sine law. The ambiguous case looks like this. If you've got a side or a couple sides and an angle across from one of the sides, you can actually draw 2 different triangles. You can draw one that's acute and one that's obtuse. If we put the 20s here as the top side, the 11s could certainly, the 30s and the 11 has to go across from each other. That's the only thing that matters. And we actually use the sine law to find this angle first. Sine law says that we can divide these guys by each other and divide these guys by each other. So we set it up like this. Sine A over 20 equals sine 30 over 11. Sine A equals 20 sine 30 over 11. So sine A equals 0.9091. And the angle there is just 65 degrees. We just take the sine inverse 0.9091. Notice that it would be the exact same work, sine A over 20 and sine 30 over 11, for this triangle over here. So we actually can find the other angle by subtracting from 180. This answer here, when you get to this point in the question, my animations are a bit off. If you get to this point in the question, this actually has 2 possible answers that'll work in a triangle. 65 and 114. Those are 2 possible answers to sine theta equals 0.9091. We know that actually from the cast rule, like from the angles in a circle. There's 2 angles that'll give you a positive ratio, and they're in the first 2 quadrants. This is the ambiguous case. This is really the only new thing from grade in grade 11 from grade 10, and we just have to be careful now because we actually didn't use obtuse triangles in grade 10. We only looked at acute triangles. So with obtuse triangles, we always have to be careful when we use the sine law, when we use angles with, or find angles with the sine law. So when do you care about this? When you have sine theta equals a positive number. There's two solutions that could work in a triangle. And this is really whenever we're finding an angle with the sine law. And we always ask, could the angle be obtuse? So practice that. There's only a couple questions. And then we'll actually practice doing three-dimensional triangles in the next lesson.